Okay, hello, welcome everybody for this episode 3 of the Science Saturday. We are going to be talking about something I'm calling mechanical art. It's art that you can generate with the help of some simple devices, and we will talk about some of the physics and mathematics behind it. And I'm sure all of you as kids have seen something called the spirographs. The image one on the slide here is sort of an image of a spirograph. So you have a circle and a big circle and a little circle and a rolling inside, and the gears on there allow you to
Dr. Kapale, there
control
is
things
some
without
interference.
slipping. So you want to control, you don't want to have any slipping, otherwise your drawing would not look very nice. And then one of the holes in that little circle, you can put a pen through it and trace a nice looking curve. Now drawing those by hand is not possible, but with this little aid like this, you can make really cool art. And I will, towards the end of the sessions today, I will give you tools and tips on making your own graphs. In fact, even videos like this one on the computer. And then the picture 2 on the slide shows something called a harmonograph. And I will tell you a little bit about those. Those are similar in some sense with spirographs, but they're a bit different as well. The similarity comes from the basic phenomena that's occurring here. Some sort of a phenomena which is periodic, repeats itself over a certain period, every let's say seconds, and that repetition is what allows us to create these really cool pictures. So there is art, and of course art doesn't mean you repeat the same thing over and over again. You want small variations. Whenever it comes to art, the beauty in the art comes from small variations that you can easily achieve. Every time you try to do the same thing, you're going to try to get a result that is slightly different, and that's where the art part of it comes from. And we will now, let's give you a brief outline. I'll talk about the pendulum motion, which is sort of the basic periodic meaning something that repeats in time motion. Then we will talk about the Foucault pendulum, which is a variation of which, we of course don't have one here. It takes a lot of effort to build one, but I will hopefully try to get the concept across so that you see that Foucault pendulum actually is a simplest structure that you can build that can make a spirograph for you if you build if you allow it to make drawings. Then we will look at some of the basic mathematics of curves, and I will help you get acquainted with tools that you can use in your own time to build these things or to make these graphs or create those animations. Then we will talk about something called a double pendulum. I'm calling it north, south, east, west because it's easy to see the two sort of perpendicular directions when you think about something going back and forth in north, south, and something going back and forth in the east, west direction simultaneously. We'll talk about then harmonographs, and then we will talk about these so-called roulettes, which are essentially curves created by, just like we saw for the spirograph, one circle rolling either on the inside or on the outside of the of another circle. And then we will look at the physics of spirographs. You can make more general structures with spirographs. So we'll do some art with spirographs today, and then I will tell you a little bit more about mechanical applications. These things are not just for fun or because they look beautiful and so on. It turns out they have tremendous amount of applications. And if you will allow me to sort of say that, trains, the steam engines, for example, were kind of an important component of the progress that we made as offshoot of the Industrial Revolution. They would not have been possible without the kinds of things that you're seeing here with the spirographs. Next slide, Atharva. So my son Atharva is also joining us today. and he's helping me with the slide. So this slide here in particular shows simple pendulum motion. We call it in physics simple harmonic motion, because it's the simplest motion you can have that's harmonic, meaning it repeats. But I'm going to call, for the purpose of today, just pendulum motion, right? And so on this top slide there, so we see a pendulum which has, let's say, a sand cup at the bottom. And if the pendulum goes back and forth, and I'm going to show you a pendulum, real pendulum here, it drops that sand down on the ground, and it is creating a nice looking, a pattern, which I will name later, and I will help you how that comes about. On the second picture there, you have a block connected to a spring, and it's going up and down. And physics students will kind of understand this, the concept of the phase space. We don't need to go really into the details, but if you plot a graph of the position of that mass as it goes up and down versus its speed at different points, you can see when it's at the bottom, the speed is 0. At the top, the speed is 0, because it's just about getting ready to reverse its direction. And so you can see there is a variation in the position as well as the speed of that. And if you plot a graph of that, it gives you the circular picture that you see over there. So now it's time for the pendulum demo. So let's get set up for that. You will be hearing me from my phone here. So you can see a mass that is connected to a long rope that's hung from the ceiling. And what I'm going to do now is hold the mass and hold it in such a way that it's aligned with the meter stick that I have kept on the ground. And there's a reason why we are doing that. It will be clear in a moment. So I'm just holding the pendulum right now as tight as possible, so that it maintains that tension, because I'm trying to maintain the direction of the pendulum. And okay, so I'm just going to release it now, and you could sort of see that it is going back and forth more or less along the meter stick that we have down there. I'm going to also give you a quick side view, if you will, of the pendulum here. And you could see that going back and forth, right? So what's happening? Imagine there was a pen attached to the bottom, and then there was a paper that was going to make a drawing on that piece of paper. You will just get a line that goes back and forth. So you're not going to really see anything remarkable if you were to do that. But if that tape, paper tape, was about to slide, let's say if it had the ability to slide slowly in this direction back and forth, so not in the same direction as the pendulum, but in the 90 degrees direction. So let's assume pendulum is going right now is going north-south. So if you had a paper or a tape that could slide in the east-west direction, then you would make a graph that we had seen on the SPAD app that all of you can download if any kind of device that you have. It works on a computer, it works on your phone, it works on any kind of device. It's called Desmos. For the computer, you can even do a web version of the app. And so that's what I have done. I use the web version of the app to look at the basics of the motion here. So again, what I'm trying to show you here is you have the east-west direction. Okay, you can see I'm moving the graph in the east-west direction and the north-south direction. And the 0 point in the center, think of that as your home, and you're basically going back and forth on the east-west direction or north and south in the vertical direction. So let's read this stuff here. So then we are going to basically just study this pendulum motion. So the graphs on here, I have already made the functions that we need. So let me explain to you what I mean by functions, right? in mathematics, the term function is used to represent a quantity that changes based on a certain parameter, how a parameter varies, right? So that's what we are kind of trying to do. And in this case, in the case of a pendulum, what varies is time. And so you can see, for example, this graph, when I turn it on, I have to do it. Okay, when I turn on this graph, you see a little dot on there, and it doesn't really do much. It's about at -5. And when I play here for the time, and when I start varying the time, I'm going to go get the slider back here. And when I play the time, you can see it just goes back and forth. So think of that as the shadow of the pendulum, or the pen at the bottom of the mass drawing something on a piece of paper. Nothing remarkable, just goes back and forth. So let's stop the time now for that. And what we're going to do now is think about what happens if we make it go in the north-south direction, right? So I'm going to turn the other dot on and turn off the first one. And you can see you can easily do that by just clicking on the little button on the left of the graph. And let's turn the time on. And you can see it's now moving in the opposite direction, or the perpendicular direction, north-south, as opposed to east-west. So I'm going to turn that off as well. Now imagine a tape. Sorry, we will stop the time. Imagine a tape that is sliding, so we can get an impression of how the function behaves. And so we're going to get this. And to kind of connect it with this, I'm going to turn the time on as well. Okay. So as the pendulum goes back and forth and the tape slides, you're going to get a graph that just goes back and forth. And again, you can see it's periodic. If I'm at 0 and at a little distance after 5 there, after that's a one full cycle. Let me zoom in on and just show you one full cycle here. Okay, so start from 0 and then close to 6, you have one full cycle complete, and then it repeats itself. So let's go back to this screen, and then let's stop the time now. So you can see this curve in mathematics is called the sine function. So we have come to sine function. Normally, if you learn mathematics, it comes from the study of triangles through geometry, but here we're just taking sine function as something fundamentally that arises from a pendulum motion. Okay, so that's that sine function. Then there is a similar function called a cosine function, which if I plot at the same time now, you could see that it is slightly shifted. It has a different color, so you can see the difference between them. I turn off the sine function, and you can see the cosine function. Let's turn it on again, and you can see they're slightly shifted. So the cool thing about this cosine function is you can actually generate it from another sine function. And that's what you see on this graph here that I'm just turning on. You can see, number 16 on the screen. You see a graph there that is a sine function, but I added a little shifter there, which is called a phase shift, but we don't need to worry about the technical terms per se. The idea is that whether I have a cosine function or a shifted sine function, they're about the same, right? So I'm going to use sine function in one direction and cosine function in the other direction. So let me turn off these graphs and then show you what happens when I do that, right? So you could see any point that we plot on this graph, it has two numbers that have to go with it. How far it is from home in the east-west direction and how far it is from home in the north-south direction. And those are the two numbers here, for example, in number 18, those are the two numbers that are depicted in there. So first, just pair of numbers. First number is the east-west direction, and the second number is the north-south direction. Okay, so now we have to turn the time on because these are dependent on time. So let me turn the time on, which is here. And you can see, sorry, go back. And let's give me just a second. I think I turned something. Turn that off and turn the time on. And you can see it is, let's make the time go a little slower. So we can, okay, I think that's the slowest it can go. And you could see that point, which is basically oscillating back and forth in east-west as well as north-south, looks like it's going in a circle. And so that's how we can achieve circles. So this relation here, number 18 that you see, sine as the east-west coordinate and the cosine as the north-south coordinate is going to be important for us later on. So kind of keep that structure in mind. You don't really need to worry too much about it other than just that. Okay, so here is the east-west motion. And let's also see simultaneously the north-south motion. And you can see all of those things are shown there simultaneously. It is moving a little faster than I would have liked, but you can control the speed. And these files that I'm playing with will be shared with you, so you can play with things in your own time. You can play with the sliders. You can change the range for the sliders. You can change the steps. And so you will be able to play with these things in your own time. So the idea is to give you tools today to play with these things later on. And then I want to give you one other mathematical form here. You don't, again, need to remember that, but it just tells me another way to represent a circle. So I said earlier that we are the oscillating point in two perpendicular directions, east, west, north, south, goes around a circle. I need to prove that to you, so I need to draw a circle. So that's what I did here, drawn the circle to show you that it's just going on that circle. Okay, so that is the sine, sort of a introduction to mathematics through physics. Right? We looked at sine, cosine, and then how we can put those sine and cosine functions together to get a circle. We're going to now change gears here a little bit and come back to the PowerPoint slide, because I want to take this two perpendicular. I want to take these two perpendicular motions a little further and point out okay, so we did the demo of the math curves. If we have two perpendicular curves like that, two oscillations that are in the two perpendicular directions, east, west, north, south, then you can do something cool called, generate something that's called Lissajous figures. Really cool, and there are two examples here on the slides. First one here is kind of a very old method of generating those. So you have a very sharp, a bright light beam coming in, and you have a tuning fork. And if you have seen a tuning fork, they're used in music, analysis of music, or tuning the pianos. Tuning forks are a very good tool for that. So they put two tuning forks oscillating in one direction and the other one in the perpendicular directions, connected to mirrors there. And so the light beam then, because of the two reflections, it is able to oscillate in these two perpendicular directions simultaneously. And it gives you a very interesting curve on the screen here. There is a simpler way to do that electronically, and that is using two function generators. These are basically electrical instruments that allow you to generate voltages that can vary the sine, or that can show the sinusoidal variations, the sine graph that we saw earlier. And then you can couple two of them and make them mixed up, so that one causes the electron beam to go up and down and sideways, and the other one. And so combined motion of that gives you these. And so we have again, the equations are shown here if you're interested in those. You don't always need to know that, but all that you need to know is that you have a sine function and in the two perpendicular directions. Let's now take you to a demo of the Lissajous figures with the help of the electronic instruments that I just mentioned. Okay, so we have the first function generator here. Just a second. Okay, having issues. No, you can see that now. Okay, all right, so very good. So we have the first function generator here, and right now it is showing about 1000 hertz. That means the signal is oscillating 1000 times a second. And I have the same thing on the other function generator here. It's showing 1000 as well. And then as a combined effect of that, we are going to get a graph on the screen here, which shows like a circle. Now there is, of course, even though electronics shows 1000 hertz on both sides, there is a slight variation in those frequency. So you don't have a stable picture of a circle there. It is swishing around, it's moving around, getting squished. So there's a perfect circle there, and then it starts squishing around in the other direction. You can see it does things more interesting when I start adjusting the frequency a little bit. So on the vertical frequency, which is up and down, I'm going down a little bit, and you can see that that circle now starts moving, right? And if these two frequencies have they are the same in the beginning, so you get these nice looking curves. Steady. And if I keep going down I keep changing the frequencies, and those frequencies are very different from each other, you can start getting very interesting pictures. So here's basically close to a circle, but that's getting oscillating, oscillating very, very much. It gets more interesting when the frequencies are widely different and they don't have any integer ratio among them, right? So here is, for example, a nice graph that almost covers the whole square there, but there is an internal pattern that you can see. Now, of course, the way it looks here on the oscilloscope, which is the instrument I'm using for showing you that graph, and what's being broadcast to you is slightly different because of the frequency interplay of how fast the screen refreshes on your computer versus how fast it's moving here on the oscilloscope. Okay, so you could see there, you could see internal oscillations that don't actually exist on the oscilloscope when you look at it directly with your eyes. Okay, so I'm just going to play with these numbers, and then let's see what happens if I match. So right now I'm at 960. I'm going to quickly go down to maybe about 900 or so, and let's see what happens. We should start seeing slightly less busy pattern there when I go to 900. And you can see that pattern is more or less steady. It's slowly varying, but that's the pattern that you're supposed to, this is the pattern you're supposed to get, and then it keeps slowly varying from that basic pattern. Let's go quickly down to 500. Okay, so I went, well, I'm close to 250, so let me do 250. So 250 in the vertical direction. That means I'm going to get these endpoints here, 1, 2, 3, 4, because I have the frequency 250 times 4 matches with the frequency in the horizontal direction. Okay, so that's how you can kind of judge and try to figure out what that pattern is doing. 1, 2, 3, 4 times the frequency in the vertical 250 matches with the 1000 on the other side. Okay, so that's kind of how you can judge these patterns. Let's go to 500. So you can kind of guess now what pattern you will get for 500. It is going to, because the vertical frequency is what I'm manipulating and changing. You should get a figure 8 pattern just like the ones that I had shown on the slide there. Okay, so I'm approaching 500 now. It's 450. And you can already begin to see figure 8. It's oscillating too rapidly because the frequencies are not there yet. And I get very close to it, it stabilizes, and you get a figure 8 pattern, basic figure 8 pattern, which shifts slightly because of the internal differences in those two voltages that the electron beam in that oscilloscope is getting. Okay, so that is the Lissajous figures. Let me now show you another cool demo of these two perpendicular oscillations. Okay, so what we are going to do now is look at a pendulum. Again, another type of pendulum, which has a little, very sharp, very sharp bottom, so it can trace patterns on sand. And I'm going to just connect it to a little device here. So you can see we have a bed of very fine sand here, and I'm going to attach the pendulum here so that you can see. And then I'm going to get it to oscillate. If I just get it to oscillate in one given direction, I'm not going to get anything interesting. So I'm going to try to shift, tilt it slightly as I start it, and then you can see it will start making patterns. So in the beginning, just something very similar to the Lissajous figures, simple oscillations in two directions. Okay, right now I think the sand is not fully level, so when the pendulum slows down, it will start making those patterns. So you can see it is making kind of like a circle, almost an ellipse, right? A squash circle, if you will. But with real systems, real physical systems like this pendulum here, there's always friction. And as a result, you are going to get a pattern that's going to get smaller. So the square that we saw on the oscilloscope, that square eventually starts to get smaller and smaller in both the directions. And that's kind of what you are seeing right now on this. And you can see it makes a very nice pattern on the screen, on the sand, but it keeps, it gets small. It is going to get smaller in the horizontal direction. So my initial starting point wasn't very good. It's moving a whole lot in one direction compared to the other. But let's observe it for a second here. Now it's almost made a line. And if you look at closely on at the edge of the pattern there, you can see much finer structures there, and these structures get automatically created. And every time you do this, every time you swing that pendulum, you're going to get a nice different pattern. So this is art, which is arising out of the mechanical motion of a simple pendulum. Okay, so very cool. Every time you do this, you're going to get very, very different results. And let me see if I can zoom in a little bit more on this to show you the finer, really fine variations that you see on the edge there. Okay, you can see very, very small and changes in the surface of the sand and making these tiny heels and so on. So this will keep on going for a little bit. I want to now take you to the pendulum that we had, and I think it has almost stopped. But I was hoping to show you that the direction in which the pendulum oscillates has changed, and you can kind of begin to see that even now. The direction for the initial oscillation was this. Now it has tilted slightly, and the reason for that tilting, it happens over time. To be able to observe it, you need to eliminate friction as much as possible, which of course I don't have much control over it. We're hanging it from up there, and the rope connected to that hook there is tremendous amount of friction. We need to make that mechanical arrangement slightly different to reduce friction. And if we could do that, you will see that the pendulum actually changes pattern quite a bit. So let's go back to the slideshow there, and I will talk to you a little bit more about the pendulum itself, a long, really long pendulum rotating and changing its direction as an example of something called a Foucault pendulum. And it is an important, one of the early, if you will, experiments that showed that our Earth actually spins on its axis. So you can measure that. There's another cool thing you can do with the Foucault pendulum. And let's go to the next slide. So we talked about these Lissajous figures. Let's take a little break here in the sense. We already saw the demo of the Lissajous figures with the oscilloscope, and here's just some, a sample patterns that you can generate with this. So this is in some sense electronic art, if you will, with the help of, we saw the mechanical harmonograph, so let me explain to you a little bit what we saw, this metal pendulum making a pattern on the sand there. Because you have the internal friction energy getting dissipated, you get interesting patterns that are not quite spirographs, so we're not there yet. These are called harmonographs, right? They're generated by mechanical motion. And I will show you an example device that you can actually build later in the slide. I'm going to show you a resource. If you are interested in building one, you can actually build one. So here you can see there are 3 pendulums. One pendulum here that controls the east-west motion, the other pendulum that controls the north-south motion of a pencil that can be lowered onto a piece of paper, which is connected to a platform, and that platform itself is on a 3rd pendulum. So you can actually combine the motions of 3 pendula, and you get a harmonograph. Again, which looks kind of like this. So this animated GIF on the screen is showing you what's happening, and you can see because the strength of oscillations, which is called amplitude, it dwindles because of friction. You get these graphs that are getting smaller and smaller with time, and then they're going to slow down. Okay. So this is something you can do. Here are several examples of harmonograph. You change your initial conditions a little bit when the pencil is placed down on the paper. You are going to get a slightly different picture every time. And this slight variation is what makes it art, right? Because every time you try it, it's not something that physically you can control. Let's say I want to get this pattern number 2. Every time I try it, very difficult to replicate, and that's what makes it art. That's what makes it really, interesting. Just the simple mechanical periodic motion giving rise to this interesting artistic drawings that you can make. And my plan is to build one for the department. So next time when things open up and you are able to visit the physics department, you will be able to see one of those harmonographs in action. So let's talk about the Foucault pendulum now. Of course, all of us know that Earth spins on its axis, an axis that goes through the north and the south poles. This rotation or the spinning of the Earth's axis is what gives us the day and night, right? So we all know that. So we are, in some sense, in a lab that's spinning continuously at a given rate. And as a result, that spinning has to somehow manifest if you have the right kind of structure. So here's a picture on the top. It's a picture of this Foucault pendulum, just kind of like the pendulum that I showed, but manufactured in such a way that it has very low friction, so it does not lose energy over time. And it traces sort of like a graph that we saw with the, that you can create with spirographs. And we're going to talk about spirographs in detail. But what basically happens is the plane of oscillation of the pendulum, it does not stay constant. It keeps flipping around. And how long does it take for it to complete one 360-degree circle? Depends on your location. It depends on the latitude on which, at which the pendulum has been built. So if somebody abducts you and you want to find out where you are on Earth, you can at least figure out your latitude, if not the longitude, by building a long Foucault pendulum and observing it over time and figuring it out its period. And then you need to do just a very simple math manipulation to figure out your latitude. It directly gives you your latitude. And so you can figure out where you are. So, I don't want anybody to get abducted, but if you need to know some science tools to be able to figure that out, and you can do that. That's something cool about these Foucault pendulums. So look them up, look up Foucault pendulum on Wikipedia if you would like, and then you learn more about it. So let's move on. Let's talk about these roulettes, and I will explain the statement here in a simple language. So roulette, this is kind of like the definition. Whenever you are learning something new, you're learning words. So for the young ones in the audience, always try to focus on the vocabulary, learn those definitions. That's how you learn a new language. Science is, in some sense, a new language. And in fact, if you go deeper, if you ask a physicist, they will tell you that mathematics is the language of physics. So mathematics, it turns out, is the language of a majority of the science. And you need to understand that language, right? So the idea here is to kind of explain to you what roulettes are. Roulette is just a curve that is traced by a fixed point, okay, a fixed point on a closed curve. So like a disk, okay, let's show you a little something here. Okay, so I'm going to motivate it through this spirograph. I'm sure you have seen this. I got this kit from Amazon. You can get one for yourself as well. Pretty cool. They explain to you how you can make different drawings. You can see different colors on there because you can use you can change the pen and you can get, pretty cool things. So what's happening there is, let's go deeper into it. What you do with that is, give me just a second. So you have a larger curve, a circle, and a little circle inside. And as this little circle inside rotates, your pen will make interesting patterns on the curve, so on the piece of paper. So let's connect that with the definition of the roulette. So roulette is a curve traced by a fixed point on that inner circle as it rolls without slipping. And normally, if I had these flat edges, I would be slipping as I'm rolling also. So to avoid that, the spirographs have these gears. Okay, so that brings up connection with engines and stuff, right? Because most of our engines, whenever we want to transfer motion from one place to the other place, we need to use gears. Or if you want to manipulate the speed, gears, right? Your car, when you're on a highway, you use gears to change the speed, because you change the size of the tooth wheels that are transmitting the motion, and that allows you to do that. And so if you do that rolling without slipping, you get these patterns, and these are called roulettes. So let's move on to the next one. So I told you these spirographs, that's what they allow you to do. And again, play with these spirographs. It takes little getting used to. So this is, I think, a good opportunity for me to show you a couple of spirographs that we made with the help of the kit that I have. So I made this one. So it takes, again, like I said, it takes some getting used to. Let me see if this is going to work. If not, let's try something else. I'm going to switch the camera. So I'm going to switch the camera to show you these things a little better. Okay, so what you're seeing right now is the first attempt by my son Atharva. You can say, because I said you want to control the slipping, and if you slip, the diagram is gone. The art and the beauty of it is lost in some sense. So first attempt did not quite work. Then he tried another one, and the blue one worked quite well, but then he left midway the red one because, again, the inner gears slipped. I don't want that happening. But of course, sometimes in the middle of the process, if the wheels slip again, you get this kind of doubling pattern. I'm not sure whether this is because he did not complete the pattern or it slipped. I think he did not complete the pattern. If he had gone on to complete it, you would have gotten a much nicer structure there. And here I did a little attempt earlier today with 3 or 4 different spirographs made with 2 blues and two red ones. And you can see even in the beginning here, I slipped a little. So you see the extra line that should not have been there. And that, of course, takes away a little bit of the beauty of the drawing. But with some practice, you can do this. But later on, I'm going to give you a technique and trick which will allow you to make these without having to rely on this spirograph. You can make much better graphs, much better pictures, or even videos of these on the computer. And I'm going to do the slideshow and see what's up next. Okay, cycloid. So the first simple example of these roulettes is a cycloid. This is something you can observe in everyday life. I think in the interest of time, I'm not going to show you the actual bicycle wheel doing it. We're just going to now point out what happens. So we have, let's say there is a bicycle wheel and a small part of it is painted blue or red. And then you get this, you get a pattern like this. So let it complete that. Okay, so it completes that pattern. it makes that pattern, and that pattern is called the cycloid. And here's a little expression for this. So X is the east to west motion, Y is the up down motion, the north south, if you will. And you can see these, our favorite sine and cosine functions are coming, because you have a circle rolling, you're going to get the sine in the X and cosine in the Y. Our circle, old circle, remember that. But there is a small change. The small change comes because the wheel is moving forward with time, and that's why you have the radius times t. Radius is the radius of the wheel, the size. So that's coming up in the X direction. In the Y direction, you don't have any time dependence as much except for this. So that's the function of the cycloid. Cycloid happens to be very useful in physics as well. If you take a particle and just drop it under gravity with certain initial direction, so it's not just coming straight down, it's coming at an angle, the curve that it is traces naturally is a cycloid. So instead of doing the bicycle wheel cycloid, which does that, it actually does a cycloid that's upside down. And so that's another reason where cycloids are useful. Cycloids are something that, for example, students in my physics class mathematically prove that this is the statement here. So point on the circumference, you get these cycloids. You get two kinds of cycloids. One is called the HypoCycloid, where the circle, so these are similar to the spirographs you can make, a small circle rolling inside of another circle without slipping, and the point on the circumference that's highlighted here is making that diagram. If instead you take that circle and put it on the outside, you're going to get something called the epi. Okay, so remember the prefixes. Hypo is inside, epi is outside. Don't worry about the equations just yet. I will explain to you what's going on. They are again very simple to understand. So let's take a look at the hypo, for example. Because it's happening inside, the distance of the point is not quite big R. Big R is the radius of the big circle. Little r is the radius of the little circle. So that's just a measure of the size, right? And so because you're inside, you get r minus r, but you get cosine theta in the x, sine theta in the y. So you basically get, again, the circle rolling, right? The circle that we talked about, that is coming out because of that. And because the small circle itself is rolling as it's going down, right? So the first part of these equations tell you how is the center of the inner circle moving. It's going around a circle. And so you get the first part, sine theta and cosine theta. Don't worry about the r minus r so much. And the later part, the circle itself is rolling by a certain angle that's proportional to the ratio of these two. So we don't worry about this again. Again, you get another circle rolling. So you get a cosine term and the sine term, right? And so it's a combination of these two periodic motions is what gives you this very interesting pattern. On EpiCycloid, only thing that changes is the sign of where r is, because you're outside now. This circle, center of the smaller circle, is going in a larger circle. That's why it's r plus r. And again, you have your favorite cosine theta and sine theta functions giving you this periodic motion. And the second components are coming because this small circle itself is rolling, right? So very, very simple things to understand. Actually, based on the conceptual buildup that we saw. More general curves are where the point that you are tracing doesn't have to be on the circumference. If it's inside or outside, inside, that's where you get these spirographs. So the spirographs are actually called trochoids. That's the more general name for them. But you don't get this kind of a spirograph very easily with the kit that you have because you are limited in the bar. You can see this extent of the bar. The point that's making the drawing is outside of that circle, right? That's very difficult to achieve in the spirograph kit that you get. So these are called the HypoTrochoids. And then you, of course, can build similarly the empty ones, which are outside. So let's actually now do demos of this with Desmos in the next 10 minutes or so. And that will allow us to so we're going to just do a little manipulation here. Okay, very good. So you can see my iPad screen now, and I'm going to share the calculator with you. And so I have lots of these figures. So I have a graph here that allows manipulations of the Lissajous figures. So let's control the frequencies. Let's just control one of them. And then you can see it makes those different patterns, right? So I will be sharing this file with you so you can play with these in your own time. And all you have to do is hit the play buttons and play with those. And you can even save those graphs and images that you get by doing a screenshot and such. When I share these files with you, make sure you make a copy before you start editing them, because I don't want to lose my original work. Then because you will be basically connecting with the same versions that I have created. So you can create and save your own versions, and then we go from there. So let's take a look at the cycloid. I also made a cycloid quick demo for you, and you can see all I have to do is play with this, the A, which is the angle of rotation, how much the small wheel has rotated on a level road, and you're going to get this. Right? So in this case, you have a track that is a level road and a wheel that's going around, and it generates that cycloid pattern. And you can also make it come back, right? In real life, things like this don't happen, but you can make it come back here because there is no, so to speak, energy loss. So let's take a look at EpiCycloids. And again, same idea, those mathematical equations that you saw on the slides, you can put them in here and put them to work, and you can make these drawings. Let me make this little, oh, sorry, why is it doing this? Sorry. Okay, those of you not speaking, if you could mute yourself, that is better for everybody so that we don't have any unnecessary echoes. I see maybe, I think, Miracle. Can you mute yourself, please? Okay, somebody's not muted. Okay. All right. So let's take a look at the variations here. That's just the angle. That's the parameter that changes and makes things different. We can control the radius of the track. Okay, so we have the track, and you can see that as the track gets bigger, of course, the pattern traced out changes. We can change the radius of the wheel that's making these patterns, and you can see a variety of different things that can happen. Okay, and then there are these curves here are the ones that are making the drawing, and the files are self-explanatory. So I'm not going to explain those to you. There's graph of the wheel, for example, as it rolls. Number 10, number 12 is the shape traced out by the drawing pen. That's our drawing position of the drawing pen. And I have done this so that you can see how these curves are generated. You can turn off some of these things. So the line segment that I have at the end, you can turn that off. You can turn off the position of the drawing pen if you want. You can turn off the little circle, and then just turn the thing on to the angle variation on to generate the figures that you want to generate, right? So none of the extra distractions. You can make cool videos with this if you like. And that's very easy to, all you have to do is turn off the functions that you don't want to be seen on that graph. So that's how that works. So that's the EpiCycloid. Let's quickly take a look at the HypoCycloid, which is the circle inside, right? Okay, the radii here are a little off. So let's see. Yeah, this kind of a structure, it looks a little weird because the track is of a smaller radius than the wheel. Wheel seems to be of a larger radius. That's okay. You know, observe this. I will show you an example of such a thing happening a little later. Again, you can play with these things and change these parameters. Let me show you one of the trochoids, because the trochoids are pretty cool. Trochoids are actually more general in the sense that you can make the cycloids through the trochoid. This one is a specific case where I took the drawing pen to be at a location of 0. So I'm going to show you a very cool graphic that you cannot make with any of your spirographs. These are multiple spirographs all connected together because I'm changing the point at which is making the drawing dynamically. So you can see this little length, little drawing pen stick that you see, the stick that is making the drawing. The length of the stick is changing with time, and so you can make really cool things like this, which you cannot make with physical spirograph. So that's a nice thing about computers. Once you learn how to manipulate parameters, you can make the very interesting dynamic art, if you will. Now, of course, I fixed the distance, and when I fix the distance, this creates exactly what your spirograph would make when the parameters match. Okay, so that's that. Then let's show you EpiTrochoids. That's the last one. And then we will look at the applications of these. These things are pretty cool, all of these curves, but they're not just for fun and for the cool effect. You can make drawings out of this. This one is interesting. I want to show you the situation, let's say, where the radius is not 1, but just 1.1. When the ratio of the radii, the radius of the track versus the radius of the wheel is not an integer ratio, then you can get interesting patterns. So right now I have track radius 2, wheel radius 1.1, I make it 1.2, then you can see it makes a slightly different curve. 1.3 is more interesting. 1.5, it's going to, let's see what it's going to make. Okay, so it has more or less 5-petaled kind of structure, and then you can move on. So you can play with these parameters and learn from them. They are pretty cool. And I will be sharing all of these files with you in the chat window just right after I'm done with this. So what we're going to do now, I'm done with showing you that the graphs. Let's go back to our PowerPoint, and I want volume. Okay, so let's share the screen. Let me stop sharing here.
Dr. Kapale?
Yes.
What did you use, Mathematica or?
Yeah, so it's called, let's look at this slide here. It's graphing the curves with Desmos. So it's a very nice graphing calculator that is web-based, and for your smartphone or tablet devices, you can download the app. So you can just go to desmos.com and download the calculator, and then the files that I share with you, you will be able to use them with that. So you can do these things with Mathematica as well, and that's a little bit more complicated to use for everybody, because you can't always get access to Mathematica to manipulate things. But with Desmos, it's accessible to everybody. So I decided to use this one, and I'll be sharing the files with all of you. So let's go to the next slide. Okay, and let's take a look at some applications, right? So I'll just briefly explain to you. So when I showed you the wheel radius being larger than the track radius, this is one example of that. And it's actually used in a real engine called the Wankel engine. You could see the operation of the engine in the picture on the left. It has all of these 4 cycles: intake of the fuel, then the compression, ignition, and exhaust, and all of those are controlled by this spirographic kind of motion of the triangular looking device that's moving through this outer chamber, right? And on the right, of course, you have the actual picture of that engine. The images are taken from Wikipedia, but you kind of understand the physics and the mathematics behind it, and it's really, really cool. Another very, very cool example, and this is where I said, one of the important byproduct of industrial revolution is the steam engines, and it would not have been possible without this cool understanding of getting the translational motion out of rotational motion, right? All the engines that you build, they give you rotational motion. That's what your car does. And eventually it has to be converted to a translational motion so that you can go straight, right? Wheels rotating, but going straight. And that can be done very easily with this structure here on the left. The animation that you see is the wheel radius being exactly half the size of the track radius. And then you can see the graph that's plotted. The spirograph that's plotted is actually a straight line. It only has two cusps. And so that's pretty cool. That allows you to do this conversion of rotational to translational motion very nicely. And you can see a couple of pictures here that illustrate that in more details. Same thing here, the piston going up and down, let's say pushed by the engine, is causing the rotational motion because you have the gear ratios or the radius ratios to be exactly the same. Let's show you one more kind of a cool example of this. NASA's Fermi Gamma Ray Space Telescope is looking at Vela pulsar, and in its tracking of this Vela pulsar through its field of view over a longer period of time, it actually generates, if you will, a celestial spirograph. So let's take you there. It's a very small 1-minute video. Okay. Well, before I think it started, so let's. Okay. I wonder where it is. It must be here. Okay, there we go. So every time I clicked, it started showing me version of it, and then I wasn't able to. So Jesse, just give me a thumbs up if you can see the YouTube video. And can you hear it? There's some music.
No.
Okay, if you cannot hear the music, that is okay. Just watch the spirograph that it makes. So let's make it full screen. And don't worry about the music. There is a music track. But this spirograph is made by the image of the Vela pulsar as seen by that telescope in its field of view. So again, pretty cool, pretty cool. Okay, we can stop there. The link is there in the slide, so you can extract it later on. I'm going to close this. Let's go back to our slideshow. There is one other cool sort of astronomical example of a nebula that has been named Spirograph Nebula just because of the way it looks. It looks like a very complex looking spirograph. Let's move on to the next one. And here is another very cool example how you can try to generate these spirographs through another set of celestial data. So the idea is take orbits of any two planets, right? And you can, if you do a scale drawing on a piece of paper, you could do that and draw a line between those two planet positions every few days. And because the inner planet orbits faster, again, so you have periodic motion. Two periodic motions coupled gives you these interesting features. So inner planet orbits faster than the outer planet, you get interesting patterns. So the pattern on the leftmost picture here is Jupiter's and Earth system. So line joining Jupiter and Earth and traced over 7 orbits. The center one is Mars and Venus, 7 orbits, and Earth and Venus is much more interesting, and it has this 5-petaled kind of very cool structure. You can't make any of these things very easily with any other system. It would be actually cool to figure out what makes these 5-petal pattern. And you can do that by playing more with these patterns that we saw. Let's go on to the next slide where I show you all the resources. The top one, of course, is desmos.com, which is the website that allows you, it's basically a graphing calculator available for free. You can all download, play with it. If you want to learn about coding to generate mathematical art, there's another very cool website that you can use. I use Wikipedia for several of the pictures that I showed you there, but I have replicated them in Desmos as well, as I showed you. Some of the previous work on this is done by Carl Sims, who loves math and creates arts, and he generated several of these harmonograph kind of pictures that I showed you. There is a book on harmonographs and how they are useful actually for analysis of music and understanding mathematics of music. So there are some deeper connections here that you can explore. And if you want to build one harmonograph for yourself, and I think we're surely going to build a big one here in the department, the link for how to do that is at the bottom. So that's the picture that I showed you with 3 pendulum. So what I'm going to do now is stop sharing and stop recording as well, and then we can take up questions.